Okay. Hello. This will be the solutions for the practice problem set. All right. Let's see. All right. So let's see. Graph the following piecewise functions. All right. We're gonna need somewhere to graph them. So let's make this 1, 2, 3, 4. 2, 3, 4. 1, 2, 3, 4. 3, 4, 5. Okay. Let's see. So if x is less than -2, so -2 is here, then we have, well, okay. So the way I like to do these problems is I just kind of look individually. So -x minus 2. We'll graph this in blue. All right, so -x minus 2, what does that look like? Well, this is our y-intercept, -2. And then our slope is -x, so down 1 over 1. All right, so this is kind of what our line looks like for that one. Let's see if I can draw a better line there. Should be like, that looks slightly better. All right, and let's look at this next one. X plus 2. We'll graph this one in red. So x plus 2, 1, 2 are vertices there. And then x, so down 1 over 1. Boom. All right, let's see if this is probably, oops. I'm gonna extend this line a little further, I think. All right. There we go. All right, and now that I've just graphed both lines, we can see the, what our domains are telling us to do. So the blue line only goes if x is less than -2. So less than -2. So let's see. -2, less than would be over here. So let's delete everything past that. Oh my gosh, I deleted a lot more than I wanted to, but that's okay. Place an open circle there, since this is only less than and not less than or equal to. Get my graph back here. All right, and this one is x if x is greater than or equal to -2. So greater than or equal to -2. So -2 greater than or equal to -2 would be this direction. So we'll delete everything that's past that. Boom. That's our graph. All right. We'll try a similar strategy for this one. Oops. That's better. All right. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 2, 3, 4, 5. 1, 2, 3, 4, 5. All right. 2 if x is less than 0. So here's 0. 2 if x is less than 0. So here's the line g of x equals 2, and I'm going to stop once we get to 0, and place an open circle there, since it's only if x is less than 0. Now between 0 and 3, so between 0 and 3, we have x plus 1. What does x plus 1 looks like? Well, that's just a line with slope 1 going through the point 0, 1. So starting at 0, 1, and we're going to have a closed dot there since it's less than or equal to. And then our slope is 1. So up 1 over 1, bing. And then we'll stop. Beep. Oh my gosh, I swung that line around, that was crazy. We're going to stop right there with an open circle, since this is not equal to. And now, if x is greater than or equal to 3, we have this line, x minus 3 squared. All right, this is some kind of transformation of x squared. What kind of transformation is this? well, if the -3 was on the outside, it'd be a vertical one, but it's on the inside, so this is going to be some kind of horizontal shift. Now we didn't know, is it left or is it right? Okay, how do we know? We look at the sign. Negative, okay. Negative sign makes me think left, but it's backwards, so that means right. So negative sign is right, and this is the graph of x squared just shifted to the right 3. So let's see. X squared would kind of look something like this if we were drawing both sides, but we only need what's greater than or equal to 3, so we only need that right side. Ha-boom. That's the next one down. All right, let's look at this one. Draw another graph. That's very long. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 2, 3, 4. All right. If x is less than -1, where's -1? It's right here. If x is less than -1, -3. Okay. So let's go down 3. Here's -3. Boom. And then we have an open circle there because it's less than and not less than or equal to. All right, let's see. If x is between -1 and 2, that's what this kind of notation means. Oh my gosh. X is between -1 and 2. Then we just have a line, y equals x, or h of x equals x. So what does a line look like? Starts here, and then we go down 1, left 1, we go up 1, over 1, that. Boom. And then we have filled in dots here because it's inclusive, less than or equal to, less than or equal to. All right, and if x is greater than 2, 5. 1, 2, 3, 4, I don't have 5, 5 would be here. So if x is greater than or equal to 2, here's 2, so here's an open circle, or just greater than 2. There's an open circle over 2. 5. The graph h of x equals 5 is just a horizontal line at y equals 5. All right. The next one. Boom, 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 boom. 4, 5. 1, 2, 3, 4, 5. Okay. X is less than 1. Okay. 1 is right here. Well, okay. So this one's getting a little bit more complex with these, multiple lines and stuff. So I'm going to go back to what I did on the first one. So let's just graph the line, -2x. So I know it's going to go through the origin because we don't have a y-intercept. And then our slope goes down 2 and right 1. So this is our line here. Graph that one in black. Let's graph this next one in red. P of x equals 3. 1, 2, 3. Just a horizontal line. And P of x equals x minus 5. Okay, our y-intercept is 5, -5, so 1, 2, 3, 4, 5. And then y equals x, so up 1, over 1. Let me continue that on like that. All right, and now let's worry about some bounds. So if x is less than 1, we have this first case. So we can stop when x is greater than 1. But that includes the 1. So just put an open circle here. Boom. Okay. For our next one, we have if x is between 1 and 4. So let's see, that's between 1 and 1, 2, 3, 4, 4. So we only need those spots. So let's delete everything outside of those bounds. All right. Looks good. And let's see, do we need open circles, closed circles? We need a closed circle at 1. Done. Then an open circle at 4. Done. And then this last one, if x is just greater than or equal to 4. So here it is at 4. And we only need when it's greater than or equal to, so we can delete everything less than. Boom. And then we need closed circle at 4 because it's greater than or equal to. Okay. Oh, wow. This is a lot of work. My goodness. State the parent function, list the transformations, and graph each of the following. A lot of graphing. All right. State the parent function. I see absolute values, so I know the parent function is absolute value of x. List the transformations. Okay. Okay. Okay, the transformations. Well, I know we're flipping. Are we flipping over the x-axis or the y-axis? Over the x-axis. How do we know? Because it is outside rather than inside. Is that right? Yeah, I think so. Well, I'll graph it and we'll see. So I know we have a flip over x-axis. Let's see, any horizontal shifts? Yep, we got one. Now is it to the left or to the right? Well, it's a plus sign. The opposite of that would be to the left. So we're going left 1. Any horizontal shifts? Yep, we got 1, and we're just going up 4. We don't have any stretching or compression. Compression. So that's good. So let's graph. I will graph the parent function in black, and then I'll graph this one in red. So let's see, the parent function would look like that. Absolute value of x. And now, this parent function, we're going to flip it. I'll graph each step. So let's see, I'll graph this one in blue, this one in green, and then once we do them all, it'll be in red. All right, so flip over x-axis. Boom. All right, now let's move it left 1. Oh, need an arrow there. All right, and let's move it up 4. 1, 2, 3, 4. Boom. And if we wanted to, we could list the domain and range. The domain here would be all real numbers or negative infinity to infinity. These are just two different ways of writing them. The range would be, well, let's see. The lowest we can go is down forever, so that's negative infinity. And then the highest we could go is at this point here, which we said was 4. All right. Let's look at this one. Parent function, P for parent, seems to be square root of x. I see a square root. Okay, square root of x. I got that in mind now. And let's list some transformations. Let's see, it looks like we have some stretching, compression going on here. 2. Would that be a stretch or a compress? That would be a stretch, I think, by 2. All right, we've got some horizontal action in here. That's going to be right 4, remember, because it's backwards of what we think. It's just backwards of what I think. You know, it doesn't have to be backwards for you. You could just think, oh, -4 is right 4. I'm not like that. Let's see. -1. That's down 1. Down 1. No flipping. That's good. That's good. I don't want things to get hard. Flipping is where things get hard. Where things get hard. Let's see. 1, 2, 3, 4, 5. 1, 2. 1, 2, 3, 4. 1, 2, 3, 4. I'm going to want it to be a little bit longer on this side. 6, 7, 8, 9, 10, 12. All right. So I'll graph the parent one in black. Again, the parent one looks like this. Okay. I'll graph stretch by 2 here. This one there, and then the final one in red, because that's my favorite color. So let's see, a stretch by 2. What is that going to change? That's going to change our y values at each point. So right now we have, on our parent function, we know 1, 1 is on our line, which means that in this one, when we're stretching it by 2, we should have 2, 2. So stretched by 2, boop. Oh wait, not 2, 2. Ignore me. Don't ignore me now. Okay. So we should have 1, 1 on our original graph, on our parent function, because 1 equals square root of 1. So 1, 1 is on our line. And now when we multiply, this 2 is kind of multiplying our y values. So every y value we would output originally, we're doubling. I'll show you. If we consider p of x equals 2 square root x, then when we plug in 1, p of 1 equals 2 times square root of 1, which equals 2. So originally we got p of 1 equals 1, but now we have p of 1 equals 2 because we're doubling our y values now, which means that 1, 2 should be on this line. So 1, 2. All right. I hope that made sense. It might have. It might not have. If it didn't, it's my fault. It's not your fault, I swear. All right, now we're moving right 4. So 1, 2, 3, 4. Boop. And then we're keeping the same kind of stretching. So 1, 2. Looks good. And now we're moving it down 1. There's 1. And then we're keeping the same kind of stretching. Boom. Boom. There it is. Now, if we want to list our domain and range, which it doesn't ask us to, but I'll do it. I'll do it anyways. The leftmost point we could go, just by looking at our graph, is this one right here, that one, right there, that point, right there. Now, what point is that? That's 4. And we can include 4. Oh my gosh, look at something. There should be a bracket up here because we can include 4. I hope you weren't typing angry comments. I don't know why you would do that, but there you go. All right. And how far right can we go? Well, this arrow, he's going to keep going. And then he's going to keep going again. And he's never going to stop, which means that he can reach infinity. I believe in him. Our range Okay, how far down could we reach? Well, it seems like our cutoff point seems to be right there. How far down is that? Well, that's -1. How far up can we go? Now this line, he doesn't look like he's going up, but believe him, he goes up, and he doesn't stop. He doesn't look like he goes up very fast because he doesn't, but he'll get there. He'll get there eventually. Where will he get? To infinity, because he just never stops going up. Oh my gosh, this one looks really hard. Okay. Can we do it? I don't know. I'm certainly hoping so. Let's see. What is our parent function? Okay. What is our parent function? That'd be 1 over x. 1 over x. Now, do we remember what 1 over x looks like? Maybe. It looks like that? Yeah, I think that's about right. Okay. Now let's check out some transformations. What are our transformations? I notice we have something here. Seems like some kind of horizontal shift. Now, which way are we going? We're going left 2. And I can tell because of the plus sign here. All right, and this -3 is doing something too. What is he doing? He's doing something. He is moving us down. And how much is he moving us down? He's moving us down by 3. Down 3. Okay, so these are actually manageable. These are manageable transformations. I think I can do this. So let's see if this is our thing. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 2, 3, 4, 5. Okay, cool. All right, so let's see. I'm going to graph the parent one in black again. Okay. All right. That's looking good. I wish if I could draw like the axes a little bit better, this graph would look better, but it'll be okay. Now let's move it left 2. I'll draw that in green. So left 2, so 1, 2. So we imagine like this is where that line would go. Yeah, that's pretty close. That's pretty close as to what it should be. I just deleted stuff. Yeah, that's pretty close. I think that's good. All right, let's move him down 3. So we're just gonna shift this guy down 3. So 1, 2, 3. So boom. That's what he would look like. That one's a little sketchy, but it's okay. And let's see. Does he reach all real numbers? Okay, let's look at the domain. How far left can we go? We can go to -infinity. But can we go all the way to the right? Not really, because we have a horizontal asymptote at -1. So we can go from -infinity to -1 not inclusive. But then from -1, we could go to positive infinity. So really, we could reach everything except for -1. All right, and now let's look at our range. So I notice we can go up as much as we want. We could go down as much as we want, but we never seem to cross this line right here. What is that line? That line is -3. So our range would be all of the real numbers except for negative 3. So that'd be another way to write them, but it's probably not a helpful way to write it. All right, I don't have to graph this one, just describe its transformations. Oh, fudge. Okay, this one seems really hard, actually. Okay, so let's think about this. We have f of x, and this is a function. Okay, but we also have this thing right here, g of x. Okay, so let's consider that g of x is the parent function. Then f of x is just some transformation. So f of x is just some transformation of g of x. Okay, so g of x is our parent function. So what are we doing to g of x? Well, we're flipping it, and that would be over the x-axis. Okay, we're stretching it by a factor of 2. Let's see. And then we have a horizontal shift here by right 3. And we have a vertical shift right here, up 1. So notice, we don't even need to know what our parent function is in order to describe how it's being moved. Really, the only things that's making a difference here is these coefficients and these constants, these numbers that are actually being attached to the function itself. So in this case, let's see, in this case we had attached a positive 1 here and a plus 4 here, and then a minus sign on the outside. Here we put in a 2 and a minus 4 and a minus 1. And really, it's just the placement of those things and what we put that's describing the whole transformation. G of x kind of just, the parent function you could put in any parent function, really. All right. Given the following graphs of transformed functions, find their equation. Okay. Now, from my many, many hours of mathematics, I look at this and I can see this guy looks like an x cubed. I just know it. I can feel it in my gut. More than a feeling, though, it just looks like this. I know the one side's going up forever, one side's going down forever, and so I know it's probably an x cubed function. Okay. In the parent function of x cubed, it normally hits the point 0, 0. So it usually looks something like this. And we have the flattest part going through 0, 0. So this point is going to be very important to look at, because this is going to tell us our horizontal and vertical shift. So let's call this function t of x. T of x for transformed function. All right. And so let's see. Our function went up by 1, 2, up 2. That's one transformation I know of. It went to the left 1. How do I know it went up 2 and left 1? Because I'm looking at where 0, 0 on our parent function is on our transformed function. So I know the flat point of our x cubed function normally goes through 0, 0. And so now I'm looking at where it is. Where's the flat point of this function now? It's at -1, 2, which means that our function went left 1 and up 2. All right. Now we need to know, was it flipped at all? Well, since it's on the left going down and on the right going up, just like in our parent function, it doesn't look flipped to me. But let's plug in some values and find out. So let's say we have a times x, since we moved left 1, that'd be a +1, cubed, and then up 2 would be +2. And now let's plug in one of the points here. Yeah, let's plug in a point that's on our graph and solve for that a. Let's see, where's a good point? I hope we don't have to solve for this one. Well, that's easy. Okay. I guess we can solve for that. So when x is 0, we have y equals, let's see, this is 3, so this would be 2.5. So we get 2.5 equals a times 0 plus 1 cubed plus 2, or 2.5 equals a times 1 cubed plus 2. So 2.5 equals a plus 2. Since 1 cubed is 1, and 1 times a is a, now we just need to solve for a, so let's subtract 2 from both sides and then get 0.5 equals a. All right, great. So now that we have t of x equals 0.5 times x plus 1 cubed plus 2. That's our final function. Now, what were the steps for that? My steps are find vertical and horizontal shifts, write equation with a as your stretch value, and then plug in a point. Done. Let's try it again. With b. All right, let's identify our parent function. Our parent function is, we'll call it z of x, that sounds cool, equals x squared. All right. So z of x, x squared is our parent function. And I know on a normal parabola, it would look like this, where our vertex is at 0, 0. So let's find where our vertex is now. So our vertex has moved to the right 4, and it's moved down by 2. So I know we move right 4, down 2. And so let's write that. So z of x equals a times x minus, let's see, right 4, so that's minus 4 squared. Down 2 would be a minus 2. All right. And now let's plug in a point. So let's see, where's a good point on our graph? This seems like a fine point. So at x equals 5, we should get 1. All right, so let's plug in 5. So let's see, z of 5 equals a times 5 minus 4 squared minus 2. So z of 5 is the same as 1. So 1 equals a times 5 minus 4 is 1 squared minus 2. So 1 equals a minus 2. Add 2 to both sides, we get 3 equals a. Perfect. So we get, as our final equation, z of x equals 3 times x minus 4 squared minus 2. Let's not write a box. Let's put something cool like a smiley face, because we did it. Yippee! All right, next. Oh my gosh. What is this? Okay. What is our parent function? Our parent function is, oops, that's not right. Our parent function looks like 1 over x squared. So, if we remember, what does 1 over x squared look like normally? Normally looks something like that, right? Where we have a horizontal asymptote at 0, y equals 0, and a vertical asymptote at x equals 0. So let's look at where those asymptotes are now. Okay, well, I see that first off, our graph is upside down, because I drew it going like a tree, and they drew it going like a trench. So there's definitely a minus sign in here. We'll keep that in mind. Let's see. Flipped over x-axis. Okay, now let's look at where our asymptotes went. So our horizontal asymptote seems to be up here now at y equals 2. Okay, that gives me good evidence that we've moved up 2. Okay, let's see. Now where did our vertical asymptote go? I see a vertical asymptote right here at x equals 1. Gives me good evidence to believe that we've moved to the right one. Now, how can I tell that these are asymptotes? Good question. I hope you asked that question. If you didn't ask that question, there's still hope for you. Don't worry. Let's see. How can I tell? Well, when you're looking at the graph, get all this nonsense off here. When you're looking at the graph, you really gotta be a line whisperer, I guess kind of. You gotta look and see what they're doing and how they're feeling. So if you start, let's say, on this line and you follow him, where is he going? Well, he's going down and he's going down, but as he moves closer to 2, he starts to slow down. And it looks like if we continue on forever and ever and ever, we're always going to get closer to 2, but we're never going to actually get to 2. And so that's the definition of what asymptote. And so by the shape of the graph, I can tell that we're going closer and closer to 2, but it doesn't look like we're ever going to get there. And so that's how I know that y equals 2 becomes an asymptote. Same thing for x equals 1. Our lines are moving down and down and down, but as we move closer to 1, our line goes down and down faster and faster. So it doesn't look like we're ever going to actually get to 1, but we are always moving closer. Which is why I believe we're moved right 1 and up 2. Okay. Are we stretched at all? I certainly hope not, but we'll use the same method as last time. So it'll be okay. All right, now let's write what we have so far. Y of x equals 1 over negative a x squared. Oh, I need to consider that we've actually shifted a little, so 1 over negative a. Negative sign comes from this flipping times x minus, see, we moved right 1, so that's minus 1 squared. And we moved up 2, and that up 2 comes outside of the fraction. All right, now we have to solve for a by plugging in a point. Oh, I found an easy point. At x equals 0, we're at 1. So let's plug that in. So at x equals 0, we're at 1. So let's see. So 1 equals 1 over negative a times 0 minus 1 squared plus 2. 1 over, so 0 minus 1 is negative 1, and negative 1 squared is just 1. So we get 1 over negative a plus 2 equals 1. Subtract 2 from both sides, we get negative 1 equals 1 over negative a. Let's multiply both sides by negative a, and we get a equals 1. That's wonderful to hear. So, if we're going to write our final equation, we get y of x equals 1 over negative x minus 1 squared plus 2. Let's box that, and maybe let's box it again, because that was hard. I'm very glad we got through that. How much? Oh my gosh. This thing just keeps going. Oh my gosh. Okay. I need to hurry this up. Okay. My goodness. H of g of x. Okay, find the following. Make sure to list domain restrictions if there are any. Okay. We can do that. And by we, of course, I mean me. Unless you want to help. But you're not here, so I don't think you will. It's okay. We can't all be helpful. All right. So this is function composition here. And we read this as h of g of x. So h of g means that we do h, and everywhere we see an x, we plug in g of x. All right, so h of x is square root of x minus 1, but instead of an x, we're going to put g of x. So x squared plus 4, and then r minus 1. All right, let's simplify this a little. Square root of x squared plus 3. All right. I hope I didn't. Okay. Are there any domain restrictions? Okay. I'm about to put work down on this paper to see if it goes anywhere. But if it doesn't go anywhere, I want you to completely erase it from your minds. Just pretend as it never existed, because it. Okay. Yep. Act as if it never existed. I don't think there are any domain restrictions here. I think we're all good. I think it's all honky-dory. I think. Well, we'll call it that. And if I'm wrong, then you know, I'll be fired or something. I don't know. It's fine. So g of f of x. So let's do that. Let's try that now. So we're going to look at g of x, but we're going to plug in an f of x everywhere we see an x. So 2x minus 5. So 2x minus 5 squared, because of this x squared here. Then we add the 4. Now this 2x minus 5 squared, we can FOIL this a little. We could do some first, outer, inner, last. Some foiling. It's always fun. 2x minus 5 times 2x minus 5. I'm gonna leave. This is a fun math trick. This is a fun math trick. I'm gonna leave this this as an exercise for you guys to foil it because I don't wanna foil it right now. I'm just gonna write down the final thing. Let's see, minus 10x plus 25 should be right. 2 times should be 20. There. All right, and then don't forget our plus 4. Okay, so 4x squared minus 20x plus 29. All right, and you know, if you don't get the same answer as me, I might have done something wrong, but maybe double check your work before you tell me, because I'll be very sad. I'll be very sad if I'm actually wrong. And so make sure I'm actually wrong before you tell me, because you don't want to make me cry unnecessarily. Unless you do, in which case it's really hurtful. I thought we were friends. All right, f of x plus g of x. This is a pretty easy one to do. Addition. F of x is 2x minus 5. G of x is x squared plus 4. Let's see, the x squared doesn't have any friends. 2x doesn't have any friends. Negative 5 and 4 are friends. They add together to become negative 1. Just like real friendships. And let's see, can we factor this? I think we can into x minus 1 squared. No, we can't. Ignore that. We almost could. But it's okay. We don't have to factor everything. That's not a rule. Nobody's forcing us to. F divided by g of x. Let's try this. 2x minus 5 over x squared plus 4. Oh, fudge. You know, I really should have worked some of these out before putting them on the problem set. But, you know, you live and you learn. Hopefully. Let's see. I'll write this out a little better. So f divided by g of x is just the same thing as f of x divided by g of x, which is 2x minus 4, 2x minus 5 over x squared plus 4. Yeah. So this is good. I said make sure to list the domain restrictions if there are any. That was really, really mean of me because none of these have domain restrictions. So it was really just to stress you out, really. That's why I did it. Now let's look at g of h of x. All right, so g of h of x equals, well, g of x is x squared plus 4. H of x is square root of x minus 1, I think. Yep. Okay, so g of h of x, everywhere we see an x, we plug in h of x, so we get square root x minus 1 squared plus 4. All right, notice something here that's very fun. Square root and the square cancel. So we get x minus 1 plus 4, which equals x plus 3. Woo! All right, that didn't take as long as I thought. Now this, okay, I'm gonna be honest. This is kind of a hard question. So hard, in fact, that I'm bringing out the purple color. We're gonna need it. Okay. R of x is orange. P of x is blue. We need to estimate the following. R of P of 0, P of R of 0, P of R of -1, and R of P of 0.25. Oh my gosh. All right. So, the way we do this is by working inside out. So, for A, for letter A, the first one, we need to find P of 0. Okay, well, how do we find P of 0 with the graph? We look at the y value at x equals 0 on our graph, on our line. Okay, so P of x is blue. Okay, let's remember this. P of x is blue. Okay, so the blue line, we're looking at the blue line here. And now we need to find what its y value is when x is 0. Okay, well, here's where x is 0. What's our y value? 0. Okay, that was pretty easy. So P of 0 equals 0. Okay, and now we just need to find R of P of 0. P of 0 is 0. So really, this is just, we need to find R of 0. Okay, we could do that. We could do that. R is the orange line. R of x is the orange line. What is the y value at 0? On the orange line, let's see. Here's our y value right here. What is that? That looks like 1 to me. So R of P of 0 equals R of 0 equals 1. Check. Verified and done. Done and dusted. All right, now P of R of 0. Okay, so you might think R of P of 0, P of R of 0, what does it even matter? You know, it should just be 1. No, don't think that, because it's wrong. The order in which you do these things matters. Just like up here, when we did g of h of x, we got x plus 3, and we did h of g of x, we got square root of x squared plus 3. Same functions, just different order. You get 2 different answers, so we need to be careful of the order here. R of 0. Well, we already did R of 0 up here. We found 1, so R of 0 equals 1. So now we need to find P of 1, because P of R of 0 is 1. P of 1 is really what we're looking for. Okay, so let's see. That's the blue line. P is the blue line. Now we need to find the x value. No, we need to find the y value when x equals 1. So here's 1, and let's meet the blue line. The blue line is right here. Okay, so that's slightly less than 2. We'll call it 1.98. 32. I like to estimate out to 4 decimal points because I didn't have friends in middle school. No, I'm just kidding. Don't estimate out that far. That's stupid. 1.9 is good. Okay. So P of R of 0 equals P of 1, which equals about 1.9. Boom. Let's go to blue here. We'll save red for the last one. All right. Let's see. P of R of -1. Okay, let's find R of -1. We could do this. Okay, R is the orange line. Let's go to -1, meet the... Kind of looks like we meet here. If I drew my line better, it would look like we meet there. Let's see. Yeah, I mean, we'll say we meet there. What is that value? That's -1. Okay, perfect. So r of -1 is -1 because the y value at x equals -1, or yeah, is -1. Okay, good. And so now we need to find p of -1. Okay, so we're going to go to -1, and now we're going to go find, so p is the blue line. Okay, p is the blue line. Start at -1. Now we're going to go find where p of -1 is, and it's probably right about here. Okay, and what is this? Well, let's see, this is -4 here, so this would be -5, so this is maybe like -5.5, so -5.5. Okay, so p of r of -1 equals p of -1, which equals -5.5. Boom. And you know what? If you got things like slightly different, that's good. Maybe it's not good. It depends on how slightly different. If you said for that one -5.4, that would be okay. If you said -5.6, that would be okay. Actually, neither of those are okay. Because they're wrong. They're wrong. So I thought I was looking at this graph wrong. So that's -5. This would be -5.5, right? Because it's in between 5 and 6. So this is surely less than -5.5, or greater than -5.5, right? Since it's in between these two values. I'm sorry. I made a mistake, and now it's all confusing. Okay, so here's -4. Here's -5. Here's -6. So this would be -5.5 here. So it's in between -5 and -5.5. So anything in between that range would be an acceptable answer, which -5.5 is not. So let's see, -5.25. That seems good. That's an acceptable answer. Okay, now I'll ramble on. If your answers are slightly different, that's okay. That's okay. Because it does say estimate, right? And so, our estimation, some people are more accurate. Maybe you're much more accurate looker at graphs than I am. It's very possible. I wouldn't doubt it even. Okay. R of p of 0.25. First, let's find p of 0.25. Okay, let's see. P is the blue line. So x equals 0.25. So here's 1. Here's 0.5. So here's 0.25. Oh, fudge. This is going to be horrible. It's going to have... Oh, fudge. It's fine. This is... Oh, okay. Beep. All right. Kind of seems like right here is good. And what is that? Well, let's see. This is 1. This is 0.5. So we'll call that 0.75. Ish. So now we need to find R of 0.75. Okay, we could do this. So R is the blue line. R is the blue line. Okay. No. R is the orange line. The orange line. Okay. The orange line. Here's 1. Here's 0.5. Here's 0.75. Okay, and the orange line is at... We'll call that... So here's -1. Here's -0.5. So a little bit bigger than -0.5. We'll call it negative 0.55. Okay, so r of p of 0.25 equals r of 0.75, which equals negative 0.55. Wow, that was freaking challenging. I'm so sorry I gave this to you. No, I'm not. It's not so bad. I think you'll be able to do it. Yeah, it's very fun. I think this is good. Let me know if you need help. I mean, I know this is like all the answers and such, but you know, I sometimes say unnecessary things, or I say too little about things. And so, you know, if you need help more than these videos, I exist outside of them. I know many of you might not know that because you've never come to my session, and I'm not saying names, but I haven't seen some of you guys. And it doesn't hurt my feelings necessarily. Okay. All right. Well, anyways, yeah. I was just saying, if you need help, I exist. I'll help. All right. Yeah. Bye.